So next we have to see two more derivation, that is the capacitance of a parallel plate capacitor and then the capacitance of a coaxial cable. These two derivations are very important. So first, what is a capacitor? You know, the capacitor is a component which has the ability or capacity to store energy in the form of an electrical charge, producing a potential difference across its plate. In its basic form, a capacitor consists of two or more parallel conductive plates which are not connected or touching each other, but are electrically separated either by air or by some form of good insulating material. This insulating layer between a capacitor plates is commonly known as a dielectric. So dielectric is also an insulator. Okay. Now this is a basic theory behind capacitor. Now in this subject we have to study two derivations connected with this capacitance. Okay, this is very important. Now here I have drawn two capacitor plates, and this is a dielectric medium. As I said, it's an insulator. Okay. Now I'm assuming that the first plate, you might have seen the capacitor in our electronics lab, right? These are the two leads of the capacitor, and in between a capacitor there is a dielectric medium. Now the first plate is assumed to be placed at x equal to 0 and the second plate at a distance d with respect to this one. Okay. Now here the upper plate is having positive charge and the lower one minus charge, so the electric wave will be flowing from plus to minus, and this area is a dielectric medium. Now here for the derivation we will be making use of few terms where A will be taken as a surface area, rho S as the surface charge density. You can take rho A also as a surface charge density. Then we will start from the Gauss law. We know that psi is equal to Q enclosed, where Q is a charge and psi is a flux, integral d dot dA equal to integral rho S dA. Okay. You know, rho S is the surface charge density which is given by charge per unit area. So there's that equation 1. Okay. Now we also have another expression, D is equal to rho S. Okay, from this itself we can see that D is equal to rho S, that is equation 2. Okay. So if you compare 1 and 2, you can write D is equal to Q by A. That is equation 3. Okay, I repeat. Charge density is equal to charge per area, and similarly we have rho S is equal to electric flux density D, and if you compare these two equations you can write D is equal to Q by A. All these equations we studied earlier. Okay, we already studied earlier. Now this is also an equation which we have come across earlier. V is equal to minus integral E dl. That is equation 4. We know D is equal to epsilon E. From that E is equal to D by epsilon, where epsilon is equal to epsilon 0 into epsilon r. Okay, that we know. Now what I am going to do is I am going to substitute E in equation 4. So I can write V is equal to minus of integral D by epsilon dl, and again I can substitute D as Q by A. So minus integral Q by A epsilon dl. So here instead of dl we have to use dx, because we have assumed x is equal to 0 and x equal to d. So instead of dl you have to take dx, that is written here. Now q, a and epsilon constant I have taken outside, so integral 0 to d dx. Okay, so if you integrate dx you will get x, then when you apply the upper limit and lower limit, finally you will get this is equal to minus q by epsilon a d. I repeat here, integral of dx is x, then you apply the upper limit and lower limit, so you will get this expression. So finally we will get v is equal to q d epsilon a. Actually this minus sign is not considered since only absolute value is taken. Okay, now we have C is equal to capacitance, C is equal to charge per volume. You might have studied this expression in your +1 +2. C is equal to Q by V. That is your equation 6. Now what I am going to do is I am going to substitute equation 5 in equation 6. So I can write C is equal to Q by, instead of V I will write this expression QD by epsilon A. So that is equal to epsilon A by D. That is equation 7. And this is the expression for capacitance of a parallel plate capacitor. Okay, capacitance of a parallel plate capacitor, C is equal to epsilon A by D. I think this expression also you might have studied in your +1 +2. Clear? Then we can go to the next derivation, capacitance of a coaxial cable. Okay. Consider a coaxial cable with a cylinder of inner radius A. I have drawn two cylinders, outer cylinder and inner cylinder, and the inner one is having radius A and outer one is having radius B. We will start from Gauss law. Psi is equal to Q enclosed is equal to integral D dot dA equals integral rho V dV. So I am separating the expression, that is equation Q is equal to integral D dot dA, that is equation 1. Then we have D is equal to epsilon E, that I am substituting in equation 1. So Q is equal to integral epsilon E dot dA. Now this is having a cylindrical structure. So since it is a cylinder, you have studied E is equal to E rho A rho plus E phi A phi plus E z A z in our coordinate system. You know, in coordinate system, in a cylindrical coordinate system, the points are represented using 3 coordinates, that is rho, phi and z. So this is how you represent a vector in cylindrical system. E is equal to E rho A rho, where A rho is a unit vector, plus E phi is a unit vector, E z A z, where A z is the unit vector along z direction. This is the unit vector along phi direction, and this is the unit vector along rho direction, which is equal to E rho into A rho. Now here you have to keep the one point in mind, that is, due to cylindrical symmetry, potential will not vary across phi and z. Okay. In a cylindrical coordinate system, the potential term V will be constant across phi and z. So now you have to keep in mind what is phi and z. Z is the distance of a point from the origin to the z axis in a cylindrical symmetry, and phi is the angle between the xy axis. Okay, and rho is a distance from the z axis to the point in the cylinder. So E is equal to E rho into A rho. The reason is in cylindrical symmetry, the potential term V will not vary along phi and Z. So E phi and E Z is equal to 0. So finally you will get only E rho A rho. Please keep this equation in mind. Okay. Similarly, in a cylindrical coordinate system, we can write dA or ds is equal to rho d phi dz a rho, and dl is equal to d rho a rho plus d phi a phi plus dz az, and that is also equal to d rho a rho, because these two terms will be 0. As I said earlier, in these points or along these coordinates, potential will not vary. For this equation, please refer the coordinate system. Okay. Now what I am going to do is I am going to substitute this 4 in 5. 4 and 5 in 3. Okay, I am going to substitute 4 and 5 in 3. Okay. So finally, Q is equal to, I know here it is epsilon E dot dA. Epsilon is a constant. I am taking epsilon out. Okay. So instead of E, I will be substituting E rho A rho, and instead of dA, I will be substituting rho d phi dz A rho. This one, rho d phi dz E rho. Okay. Now I am taking rho and E rho outside. Epsilon is already taken outside. Then d phi will vary from 0 to 2 pi. This also we have discussed in our coordinate system. D phi will be varying from 0 to 2 pi, and dz will be varying from 0 to L. Okay, 0 to L. So finally, rho epsilon E rho, what is the integral of d phi? It is phi, then 0 to 2 pi, z 0 to L. After substituting all these limits, you will get Q is equal to rho epsilon E rho 2 pi into L. Okay. From that, E rho is equal to Q by 2 pi epsilon rho L into A rho. This is a unit vector along the direction rho. That is equation 6. Now we have V is equal to minus of integral E dl, equation 7. Now instead of E, I will be substituting E rho. Minus of integral, I am substituting E rho. What is E rho? E rho is equal to Q by 2 pi epsilon rho L A rho. That is substituted here. Okay. And instead of dl, what will I substitute? Here it is written dl is equal to d rho into a rho. So here instead of dl, I have substituted d rho into a rho. And what will be the limit? It will be from A to B, where A is the radius of your inner cylinder and B is the radius of your outer cylinder. Here a rho into a rho, it will be 1. And finally, you can take minus integral A to B, Q by 2 pi epsilon rho L d rho. So I am taking 2 pi epsilon L outside. So A to B d rho rho. You know 1 by rho is log of rho. Integral of 1 by rho is log of rho. So minus Q 2 pi epsilon L log of rho, limit A to B. Then you can write, you can substitute the limit log B minus log A. Log B minus log A, you can write log B by A. So this is your B. Now you know C is equal to Q by V. So you substitute this B in C. Okay. This equation, this formula you can substitute in C. Substitute it, rearrange. Finally you will get C is equal to 2 pi epsilon L log B by E. So this is the expression for capacitance of a coaxial cable.